Okay, so one thing before we get into this writing an equation for the graph of a rational function, a couple things you gotta remember. Typically I do this at the start of the year, but this year being as it is, we didn't do this. So one of the toolkit functions, one of the basic functions we look at, and you might have seen this last year, is this reciprocal function where it's 1 over whatever. And what happens with that is as we get closer and closer to zero, we get closer and closer to zero on the left, this gets to be a smaller and smaller number, like 1 over negative 1/10. Well, 1 over negative 1/10 is take the reciprocal of negative 1/10 and we get negative 10. However, if it's 1 over negative 1 over 1,000, well, isn't that negative 1,000? So what happens is we get closer and closer to zero. Why? So if we do that, as x approaches zero from the left, we know that y goes to negative infinity. And on the other side, it goes to positive infinity. So 1 over x on one side of the vertical asymptote goes to negative infinity. On the other side, it goes to positive infinity. And that's true if it's been shifted left or right. If it go left, right 1, the same thing is going to happen, except it's been shifted over to x equals 1. Okay, so that's 1 over x. They head in opposite directions. The other kind of toolkit function that we're going to deal with here is 1 over x squared, or the reciprocal squared. And what happens with that is just everything's always positive. So either side of zero, it heads to, or the vertical asymptotes, shall we say, it heads up to positive infinity, or they end in the same direction. Now, if this were a negative 1, they'd be headed towards negative infinity. But again, they head in the same direction. So this is something you want to pay attention to when you start looking at these rational functions and you're trying to fit a curve to them, or trying to fit an equation to them. So now vertical asymptotes are numbers, are values for x where we have division by 0 going on. Okay, so I see, and this is a little washed out on this slide, but in your paper it's not so bad. I see at x1, 2, 3, 4, it looks like x equals 4, I see a vertical asymptote. It looks like I see one at x equals negative 1 also. So those go in the denominator, and I treat them as factors. So I'm going to add 1 to both sides. So x plus 1 is a vertical asymptote, and at x minus 4 is a vertical asymptote, or x equals 4, there's a vertical asymptote. So I write the factor as negative 4. And in both cases, these act like 1 over x. So I don't need a square. I don't need a square with either of these values. Now, I don't know the top is 1. In fact, when I have 0 divided by a number, isn't that equal to 0? So I see this graph crossing the x-axis at x equals 2. I also see it crossing the x-axis at x equals 0. So we know from our work with polynomials that it'll be x and x minus 2 will be the zeros. Okay, and then here's like the big so what. I mean, what we've done is the big so what too, but this is even more so. If I were to expand this all out, I would know the degree of the numerator, top of the fraction, would be x squared plus some other things. And the denominator, it would also be x squared and plus some other things. So if out at infinity, all those other things don't matter. It's the squared term that's going to rule. That's going to dominate the whole equation, both top and bottom. Well, isn't that just 1? Isn't x squared divided by x squared is 1? So because these are the same power, it's going to have a horizontal asymptote. And that horizontal asymptote we see is at 2. So I'm just going to stick a 2 in front. I'm just going to stick a 2 in front here. Okay, and that's an equation that when you go graph that in Desmos on a similar window, you'll see the same thing. Okay, so first one's not too bad. Let's go look at the next one. So here, I hope the first thing you're noticing, let's see, see how at x equals 2, these are headed in the same direction? So I know that's going to act like 1 over x squared. And here, it's heading in opposite directions, so that's going to act like 1 over x. So this vertical asymptote's happening at x equals 1. This vertical asymptote is happening at x equals 2, and I can't divide by those numbers, so I know at x equals, negative 1, this I should have said. So x plus 1 takes care of the VA at x equals 1, and x minus 2 takes care of the vertical asymptote at x equals 2. However, because this is acting like 1 over x squared, this is like a transformed x squared function, okay, shifted right too. So this is the part, if anybody's going to get anything wrong, this is the part that they usually miss. Okay, so look for those 1 over x squareds. Then I only see 1, 0 here. I see it crosses the x-axis at 1. I also see a horizontal asymptote. So if we go back and think about what I just talked about, we know it has to be the same power on top, same degree in top, same degree in the bottom. So one flag for this, that what I'm going to say next is, if we were to expand this denominator, wouldn't it be x cubed plus some other terms? So that tells me if there's a vertical asymptote, it also has to be x cubed in the numerator. And you see how this kind of wiggles through, just like when we're doing polynomials. Do you see how that kind of wiggles through the x-axis at 1? That tells me that x minus 1 cubed will get this function looking like that there. And then, because we've got an x cubed on top and x cubed in the bottom, we know there'll be a horizontal asymptote, and we know that horizontal asymptote is 2. And that's that function. Okay, now I don't see a horizontal asymptote. What I see is something that looks like this. A slant asymptote, we call that, or oblique asymptote, they call it. And the way that's going to happen is it's going to be a top-heavy function, okay? So we know this one's going to be top-heavy. The degree of the numerator will be bigger than the degree of the denominator. But let's not worry about that yet. Let's look at what we do know. I see a vertical asymptote at x equals 1. It also acts like 1 over x there. So I'm just going to write x minus 1, and I don't have to square it. I don't even need to put it in parentheses in the denominator. I also see 2 zeros. I see it crosses the x-axis at 3 and crosses the x-axis at 2, and there's nothing special going on there. They're going to be not wiggling or bouncing. So I'm going to write x plus 3 times x minus 2. And notice what I said about being top-heavy. If I were to expand this on the numerator, wouldn't it be x squared plus some other terms over x minus 1? And way out infinity, that'll also be infinity. So we know we're doing this right. Now, the only thing I got to worry about is, does it cross? If I substitute, I see a y-intercept is 0, 2. If I drop in 0, do I get 2 for output? Well, let's see here. So if I drop in 0, I'm going to get 3 times negative 2, definitely not 2. So there must be some stretch factor going on. So 2 equals, just like what we did with polynomials, drop in 0 for x, stick an a in there for that placeholder, all over 0 minus 1. So does that give me 2 times a times negative 6 over negative 1? So that's 2 equals a times 6. So I'm going to divide by 6. 2 over 6 is what a is, which simplifies to 1/3. So I could write 1/3 on top like this. 1/3 on top. Just a minute here. Well, I could write it like that, but that's a little awkward. So when you have a fractional function and you got a fractional leading coefficient, just write 1 on top, slap parentheses around that bottom, and we don't have to do anything else. Okay? So that's finding. So this is what happens when you don't see the horizontal asymptote, like they haven't traced it in like they did in all the others. You're going to find the y-intercept and see if you have a leading coefficient. You can solve for a, just like what you did with the polynomials. Then the last example of this type is this one here. And what I want to draw your attention to, because what's different about this is you see this hole in the graph. Well, the only way we get a hole in the graph, that tells me that 4 isn't in the domain of that function. So that would tell me that x minus 4 is in the denominator, but that would give me a vertical asymptote. So the way we have it just be a hole in the graph is you put the exact same thing on top. And welcome to calculus, the first couple lessons in calculus, folks. This is where this comes from, okay? Or where we're going with this, I guess. So that takes care of the hole. See, that's the hole, and that's how we dealt with that hole. And then I see a vertical asymptote at x equals -1, so I'm going to write that as x plus 1, and that's acting like 1 over x, so we don't need to do anything fancy with squaring. I also see an x-intercept of 2, so it's x minus 2 is also going to be a 0, and it's just passing through. So now I see a horizontal asymptote of y equals 1. Do I have a same power? Yes, I have an x squared over an x squared, so that tells me the horizontal asymptote is going to be 1. I don't even have to write a 1 there. Let's say you didn't notice that. Let's say you didn't notice that. And I said, oh, well, here's a y-intercept of 0, 2. If I drop in 0, do I get 2? Well, if I drop in 0 here, let me go to different color ink. If I drop in 0 for all those x's, let's see, the -4's cancel out. -2 over 1 is -2. Yep, that checks. Okay, so we didn't need to do that, but it certainly checks as a way to check, okay? So y equals 1 is our horizontal asymptote, and that function without the blue writing is the 1, okay? So the other thing I'm going to have you do is I'm going to give you a description, and you need to write a function for it. And I'm sorry this font went so weird. This is x-intercepts at 1, 0. Did you see how I don't know if it was in Word or what I did, but it certainly didn't write it right. So technically those should be inside. Those are ordered pairs. Those are points. So I see vertical asymptotes at -4 and at -1. So x plus 4, x plus 1, because that's where we keep those aren't in the domain, right? That's how we get the can't divide by 0. And then I see x-intercepts at 1 and 5, and so x minus 1, x minus 5. And then they aren't telling me there's a horizontal asymptote, though I know there's going to be. So I got to figure out what y-intercept is. I got to figure out what a is. So if 7 equals some number a times -1. Is it all right if I don't drop in 0 and just write -1 and -5? What I'm doing is I'm replacing the x with 0, right? And the same thing on the bottom. So I see 7 equals, let's see, a times +5 over 4. And then I divide by 5 over 4, which is the same as multiplying by 4 over 5. That's over 1. So it's going to be 28 over 5. And if you threw that into Desmos, that would match that requirement. Okay, let's come back and do another one. If you want, you could stop the video and try that. Though I gave you some practice in the paper, in the notebook anyway, so. Oh, let me clean this up. Let's see here. Oh, I'm yawning. Let's see. So vertical asymptotes at -3 and 6. So x plus 3, x minus 6. And I see x-intercepts at -2 and at +1. Whoops, x minus 1. And then they're telling me there's a horizontal asymptote at -2. I see an x squared over x squared. So I'm just going to slap the -2 right there. Okay. Last one. Vertical asymptote at x equals 3. So x minus 3. There's a double 0 at x equals 1. So x minus 1 squared. Now I see a top-heavy function, don't you? And the y-intercept's at 4. If I drop in 0, do I get 4? Nope. So we're going to say 4 equals a times 1. You okay with me dropping in 0 for -1, then squaring it? And then -3 on the bottom. So that gives me 4 equals a over -3. Isn't this just a proportion? Can't I just do the cross products? So a equals -12. So I'm going to stick a -12 in front and be done with it. Okay? And that would have an oblique asymptote. It would probably be headed off I don't know. It would. I had no. Let's see. Where's the y-intercept? At -12, negative. So at 4. So this looks something like this. It would be a dotted line, and it would be crossing the x-axis at 1 and 4. So it would probably look something vertical asymptote at 3. I don't know, something like this is what it would look like that. And then I don't know. Now I'm telling you that, and now I don't know. Something like this. I don't like that I don't have a 0 over here, so I'm wondering if my graph's a little off. Anyways, don't go there. This is the right answer. I know that's the right answer. My graph is off how I was thinking about it. All right, go try those exercises out of the notebook packet. I'll have my work online for those. And then you got some MyOpen Math you can start working on. There'll be 3.7 rational functions. We got a little more work to do before you get through it all, but this is half the chapter, half the unit.